Welcome everybody to the symmetry of numbers. That is a different approach for a solution for the twin prime theorem. My name is Manuel P. Rodriguez Velasco and I am a mechanical engineer. I presented this study for the first time in 2022 at the Polytechnic University of Puerto Rico to a group of professors of science, engineering, and history of science also. The twin prime theorem has been around for hundreds of years, and mathematicians like Gauss, Euler, Riemann have contributed to advances in pursuit of a solution. Before I start, I want to say that I am looking for a mathematician, expert in number theory, that can help me or that can write my work so it can be published in a journal. I have presented this to two mathematicians of the University of Puerto Rico, but they are not experts they are PhD, but not experts in the number theory field. But they have seen my work, they have find it very interesting, and they encouraged me to publish it. And one of the suggestions is to find a mathematician. So this work is about modular arithmetics, the beginning of the work. I really did it in my own way. I didn't use modular arithmetics terms, but I do it in my way. When I talk with these mathematicians, they correct me and they told me that I was doing modular arithmetics and I have to write this in a different way so it can be presented in a journal. But in this video, I'm gonna explain just how I did it. I took the prime numbers and I make a sieve for the prime numbers. For each prime number, I make a sieve, and then I made sieves of multiple prime numbers. This sieve is what I call the cycle of 3, that you can see it here. And I represent in tens, and I put in that sieve that is divided in tens the multiples of the prime number that their last digit is 1, 3, 7, or 9. So you can see it here. For the number 3, the prime number 3, this is the sieve, and it goes from 1 to 30. So 1 to 30 is because after 30, everything gonna be repeated again. If you can see here in the first 10, we have 3 and 9 that are the multiples of 3. These don't gonna be prime numbers except for the 3. That is the number that makes the sieve. And here they're gonna be prime numbers neither, that is the 1 and the 7, because it's the 10 of 21 to 30, this represents 21, and the 7 represents 27, okay? So I write in the sieve the multiples of the prime number, in this case 3. And those numbers doesn't gonna be prime numbers except for the number 3, that is the one that forms the sieve, right? And we can see here in the second 10 an empty box. This is what I call a cyclic prime 10. Cyclic because I call this a cycle because it's gonna be repeated all the time. After 30 comes from 31 to 60, and these numbers in the second row, they're gonna appear in the same way, in the same order. In the first box gonna be a 3 and I'm here, and then an empty box, and then a 1 and 7. And that goes to infinity, right? So these are the basics of this work. Continue. So you can see this a 10 full of primes, what I told you that I call a cyclic prime 10, that the mathematician, the PhD I was with him, he called it empty boxes, right? Uh, 3 and 9 are multiples of 3, and 21 and 27, they are not prime numbers, how I said already. And this is all modular arithmetic, but how I told you, I do it, I call it cycles, and you can see these repetitions of this here, right? And this is very important because we're gonna track this. Instead of tracking twin primes, sorry, we're gonna track cyclic prime terms, okay? How, where they appear and how they interact with the different prime numbers, cycles of different prime numbers. You see that in the first iteration, the last digit has the same order and the same position in the second iteration, third iteration, and this goes up to infinity. Okay, and this is, of course, modular arithmetic. As we did with the cycle of 3, we can do the same with the cycle of 7. So we are representing here the multiples of 7 that ends in 1, 3, 7, or 9. And you can see here that the only of them that are going to be a prime is the 7 itself, that is the prime that makes the cycle. Again, in the next iterations of the cycle of 7, the multiples gonna repeat in the same order, and very important, the cyclic prime terms also they repeat in the same order. But what is interesting is now when we're gonna merge the cycle of 3 with the cycle of 7. That means that we're gonna make a table like here that we're gonna put together all the multiples of the cycle of 3 and the multiples of the cycle of 7. So in different colors are here the iterations of the cycle of 3, right? And here starts the third iteration and ends here of the cycle of 3. And they go all the way to 210. Why 210? Because 7 times 3 is 210. 21 times 10 is 210. And when this ends here, all this is gonna repeat again, the same process. So we're gonna merge, what we're gonna merge the cycle of 3 with the cycle of 7. To do that, we're gonna do it until 210, that is the minimum common multiple times 10, right? When this ends, we're gonna have another, the second iteration of the cycle of 3 and 7, right? So if you see, we're gonna put in the next table all the multiples of 3 and all the multiples of 7 together in only one table. So we're gonna finish the merging process. Before we put it in one table, I want you to notice and to see that all the combinations are done until 210. I mean that each 10 of the cycle of 3 gonna be combined with each 10 of the cycle of 7 without repetition. So for example, we have here the first 10 of the cycle of 3 combining with the first 10 of cycle of 7. And we have the second 10 of the cycle of 3 with the second of the 7, and the third of 3 with the third of 7. And now here we have the first 10 of the cycle of 3 with the first 10 with the fourth 10 of the cycle of 7. And all of them are all combining all possible combinations, but without repetition. We don't want to have again a first 10 of 3 with the first 10 of 7. It's gonna be only here. It doesn't repeat anywhere else. For example, this one is the first of 3 with the seventh 10 of the cycle of 7, and gonna be here only, and they don't gonna be repeating all the cycle until it comes the next iteration. So we have 21 combinations of 10s of both cycles, of the cycle of 3 and of the cycle of 7. And When this finish, they're gonna come the next iteration. But this is very important to realize this, that we have only one combination. And it's very important to know that the each 10 of the cycle of 3 gonna combine with the 7 tenths of the cycle of 7. Not in that order, but they're gonna combine one and only one time. So the first 10 of the cycle of 3 gonna be combined with the first 10 of the cycle of 7, with the second of the 7, the third 10 of the cycle of 7, or the fourth, the 5, the 6, and the 7 10 of the cycle of 7. We're gonna combine only one time with all of them. And this is gonna be very important because that system gonna lead us to some equations, so we're gonna be able to track this. Cyclic prime tens. Okay? Spaces or empty boxes, like the PhD of mathematics start calling them empty boxes. I don't know if it is because it's that a more correct term. So here we have the cycle of 3 with the cycle of 7 merged together. And we write it like this, right? Cycle of 3 and 7. It goes from 1 to 210, and you can see the tens. We put all the multiples of 3 and 7 in the boxes. The relevant multiples, the ones that end in 1, 3, 7, or 9. In the first 10, we have the 3, it's multiple of 3, the 7 is multiple of 7, and the 9, that is a multiple of 3. Look that here we don't have multiples of 3 and we don't have multiples of 7 that ends in 1, 3, 7, or 9. From 21 to 30 we have the 21 and the 27. So we have a 1 and a 7 there because they are multiples of 3. From 31 to 40 we have the 33 and the 39. They are multiples of 3. And in 41 to 50, we have a 9. That's the 49. That is a multiple of 7. 7 times 7, 49. And it goes all the way here, putting all the multiples of 3 and 7, multiples that ended in 1, 3, 7, and 9, in the boxes. And look at this. We have 1, 2, and 3 cyclic prime times empty boxes, and we have a symmetry. The symmetry is here in the middle. Why a symmetry? Because from this 10 in the middle, all the other 10s, they are symmetrical with their corresponding 10. So the one to the right from the middle 10 here, that is 111 to 120, is symmetrical to the 91 to 100, that is the first one to the left. First one to the right with the first one to the left. How they are symmetrical? Look, we have that in symmetry, we have that the 1 is linked with the 9, and the 3 is linked, or they are complements, right? Complement of the 7. So we can see here that if in this 10 we have a number, in the other 10, that the one that is symmetrical, in this one, we're gonna have the complements of the numbers here, the symmetricals, right? So we have a 1, so the symmetry of 1 is 9, the complement, so we have a 9 here. We have a 3, the complement is a 7, we have a 7 here. We have a 9 here, so we have a 1 here. So these two 10s are symmetrical. The second one happens to, again, the same. So this one here, whoops, gonna be symmetrical with 1, 2 here, this one. You see, we have a 1 here, so in the other one gotta be a 9. There is a 9 there, because there is a 7 here, gotta be a 3 there, and there is a 3 there, right? So, and then it comes the next one, the third from to the left is a 7, so the third to the right gotta be a 3 here, and all the way, all the 10s are symmetrical. Look here, we have a cyclic prime term and empty box. So we have an empty box here because the symmetry, it holds. And it's gonna hold for any combination of cycles. You can have the cycle of 3, 7, and 11. You can put all prime numbers and they're gonna be symmetrical. For example, from the 3, 7, and 11, it's gonna go from 1 to 2300. So how this form, we can make a rectangle, and we put all the tens here from 1 to 70 of the cycle of 7, and from 1 to 30 of the cycle of 3. And the numbers here are the combinations of tens. So this 1 and 1 means the first 10 of the cycle of 3, and the second one means the first 10 of the cycle of 7. So the first number is the 10 of the cycle of 3 that is combining with the second number that is the 10 of the cycle of 7. So here is the second 10 of the cycle of 3 with the first 10 of the cycle of 7. But they don't go in this order. They don't go in this order. The order that they takes in the real number line that goes from here, from 0 to, in this case, to 210, it goes like this. Let me see. It really goes like this. Goes in diagonals, right? So you see here is the first combination is that the first 10 of the cycle of 3 combines with the first 10 of the cycle of 7 here. The second with the second, and the third of the third, and that's gonna appear here in the number line in that order. So we have here the first, the second with the second, and this one, okay? So it starts in diagonals. When it ends here, then it starts here in the same height here and go in diagonals again, okay? So you can see that we have here 1 and 4, 2 and 5, and 3 and 6. So 1 and 4, 2 and 5, and 3 and 6. This is tens. So what it means here, for example, in this one here is the first 10 of the cycle of 3 that has a 3 and a 9. It combines with the first 10 of the cycle of 7. That is a 7, and that's what you're gonna have in the box, right? In the first 10. And here in the second 10 of the cycle of 3 with the second 10 of the cycle of 7. That is a cyclic prime 10, right? Cyclic prime 10. Sorry. And so on. So that's how it goes. Let me erase this. Sorry. Let me clip this. And then we can see that when it ends here, it goes this way and this way until here, okay? And when it ends here, it goes, it starts from here to here. So this is gonna be the number 1. This will be the number 2. Here is the 3, the diagonal number 3. This is the 4. Okay. I'm gonna put another color for the 5th. This gonna be like here. Sorry, this gonna be the 5. And the 6 will start here. And the last one from here, you see, here, and ends here. If you check that with the table, it will fit, right? So it's 7 lines that is combining, and that always happen like that in diagonal. So the next combination, when it comes the cycle of 11, that is the next prime number, gonna combine with this cycle of 3 and 7, and you're gonna be able to do another box that you're gonna have all the tens of the cycle of 3 and 7 here, right? And here you're gonna have all the tens of the cycle of 11, that you're gonna have 11 tens, and you have here 21 tens until 210, right? And they're gonna start combining also in diagonals, right? Until they do 21 diagonals, because here are 7 diagonals, here gonna be 21 diagonals. So, and that's what I'm talking about, okay? And this is gonna be going from here to 2310. So really, you can put in this way, you can put any cycle you want with the merging cycle. So you have gonna be in this way, you're gonna be having what I call the main cycle. That's gonna be the cycle of 3 and 7, and then the cycle of 3, 7, and 11, and then here gonna be the cycle of 13, and it keeps merging and keeps growing. So it is done all possible combinations. And here we're gonna have the arrows, right? Combining, but you can imagine these arrows also traversing the cycle of 11 when we merged them, right? So this, I have done other videos with this, and I have explained this a little bit more deeply, right? But you can imagine, because the lines are just traversing also the, the shape of the cube, right? Because this is the cycle of 3 and 7, and here we have the cycle of 11. Anyway, we continue because we don't have to study this type of shapes yet, but here is something that could be a topic for investigation, for further investigation. I think there is a lot of things that can be researched a lot, and that's my goal, to give it to the mathematics community, and so it's available for everybody. You can check here these terms. You have it written here. You can pause the video and read it. I hope you understand. This is called flip because the 9 here was a potential prime number, but then it comes the cycle of 11, and there is now a multiple of 11 that ends in 9, this 10, so the 9 has been flipped. Doesn't gonna be a prime number anymore. Okay, that's what is called prime. Here, the 9 and the 3, because they are not in the box, they are potential prime numbers. Why potential? Because they could be multiples of other prime numbers that are not yet studied, that we haven't taken into account their cycles. So there are potentials. This is prime 10 when there is no multiples in a box. Overflip means that is a repetition of two multiples. That's overflip. And we continue. When I start combining cycles, that really is modular arithmetic, like I said, but I'm not doing anything of modular arithmetic here. I'm not putting any congruence and nothing. I'm just doing the way I did it, so you can see it. But I found a symmetry in all prime numbers. And that symmetry, already a PhD told me that's because you are taking modules that the symmetry occurs. But it's curious. I don't know if somebody has seen this in the past, because everything is symmetric in the cycles. So you're gonna be checking it. Um, there is some nomenclature here that I have already been talking about, right? So this is the term I'm using for a cycle of a prime number alone, and if a cycle that combines all the multiples of prime numbers, or several prime numbers, is written this way, right? We see the cycle of 7 here, um, and the cycle of any prime number individually is Pn times 10 times 10, and the cycle of a composed prime number is the multiplication of all the prime numbers times 10. That's the length of any cycle composed of several prime numbers. Okay. So from now on, we're going to be working with the main cycle. This is the first main cycle, the cycle of 3 and 7, because it's the first fusion of cycle of individual prime numbers. Remember, always the 1 is linked to the 9 and the 3 to the 7, and they will have always a symmetry in the middle 10, and that middle 10 will always be a cyclic prime 10, an empty box. All empty boxes gonna be symmetrical distributed across the cycle, the main cycle. The main cycle gonna keep growing. So the main cycle is a cycle that it gets bigger and bigger, that grows. It's the fusion of prime numbers in order, ascending order, starting from 3, continuing with 7, 11, 13, and all up. We don't use 5 or 2, those prime numbers, we don't use it in the main cycle. It's just 3 and up, except 5. So the first main cycle, we can call it the cycle of 3, or better, the cycle of 3 and 7. That will be the first main cycle. That is the fusion of the cycle of 3 with the cycle of 7. And then the cycle of 3 and 7 merges with the cycle of 11. So the main cycle becomes this, the cycle from 3 through 11. Is same as this, 3 through 11. So it becomes this cycle of length 2310. The length of the cycle is always the product of the primes that form it times 10. After this fusion, then the cycle from 3 through 11, that is this one also, gonna merge with the cycle of 13 to form the cycle from 3 to 13 with a length of 30,030. And this process continues with the coming prime numbers. So the main cycle is the main cycle that we are going to continue merging with the coming prime numbers, and they're gonna get bigger and bigger. But as I said, they're gonna have the symmetry, and the middle in the symmetry gonna be a empty box, cyclic prime time, right? And everything gonna be symmetric for each fusion, for each main cycle. The study of the main cycle is fundamental for my proposal for the solution of the theorem. Here we have what will be always the middle 10 of all the cycles. It will have a cyclic prime time on the middle, an empty box, and all the prime numbers, the cycles of prime number, they will have an iteration here centered on the middle, right? So the middle of the cycle of 3 and 7 we saw will be like here, this combination here, right? And within 11 here, so we see how they combined in the middle. So any cycle of several prime numbers can be decomposed in individual ones, and we can see how this makes the symmetry, because from the middle one, when it's arranged, you are adding always to each of the prime numbers iterations of the cycle of each prime number to the left and to the right until reaching the length of the cycle, and to the left reaching 0. Always the symmetry lying on the center. Okay. Here we have an important table so we understand the distribution of the cycles. Again, we have here the cycle of 3 and 7, goes from 1 to 210 here. This will be the start of the second iteration of the cycle of 3 and 7. So in this row is all the relevant multiples written here, but in this one are the prime numbers. Really, we can check that in every cycle until the square of the next prime number that doesn't belong to the cycle, for example, this is the cycle of 3 and 7, the next prime number is 11, so until the square of 11, that is 121, before that we're gonna have all the prime numbers, and we will know which are the prime numbers just looking at the cycle of 3 and 7. Or if you have the cycle of 3, 7, and 11, then you will be able to know the prime numbers until the square of the next prime number, that will be the number 13, right? That will be 13 to a square equals 169. So if we have the cycle of 3, 7, and 11 until 169, that will be here, we will know that all the prior numbers will tell you which are prime numbers and which they are not. That's known in number theory. I think that's pretty already known. And that's important. So we are mapping the distribution of prime numbers gap by gap when we merge another prime number to the cycle, to the main cycle. The main cycle starts with the cycle of 3 and 7, and then we add the cycle of 11, so will be the cycle 3, 7, and 11 as the main cycle, and then we add another prime number 3, 7, 11, and 13. So, and we keep adding gaps. So the first gap that really happens is from 1 to 49. When we have the cycle of 3, we know all the prime numbers just looking to the multiples of 3 until 49. After 49, that will be here, we do the cycle of 3 and 7, and we will have all the prime numbers until 121, that is the square of 11. Here will be the 121, the square of 11. And after that, we will have the cycle of 3, 7, 11, and we will know all the prime numbers until 169, that is the square of 13. Okay. So gap per gap, doesn't matter that the cycles get so big. We gonna be tracking that gaps because gap per gap we're gonna be mapping the composition of prime numbers. So we can see here that there is a gap here, another gap, another gap, another gap. So these are the gaps that we are mapping. And this is process that goes to infinity, but we will see that everything, there are some equations that will make everything converge. We have the length of the gaps as this equation, this the first equation, okay? So is, for example, from here, pn square until pn plus 1 square, we will have that length. We subtract, right? That will be the length of the gap, and we will always know the composition of prime numbers until pn plus 1 square. So in the cycles will always be cyclic prime terms, empty boxes. We're gonna keep adding and adding prime numbers to the main cycle, and we will have always cyclic prime terms. Because this one is the prime term, cyclic prime term of the cycle of 3. I'm gonna combine with the 3 cyclic prime terms of the cycle of 7. So when we merge the cycle of 3 with the cycle of 7, we get this, that is the cycle of 3 and 7, the one that we already saw. And we're gonna have 3 of them. But because of the combination process that I already discussed in this video, so these 3 of here, this cyclic prime gonna combine with the 7 of the cycle of 11. This is the cycle of 11. Okay. So this is the cycle of 11. Sorry by my writing. So this one gonna combine with this one, and we see that each one of them gonna combine with the 3 of the cycle of 3 and 7. Each cyclic prime time of the cycle of 11. So how many we're gonna have in the next cycle? In the cycle of 3, 7, and 11, we're gonna have 3 of these times 7 of these. We're gonna have 21 cyclic prime times. Okay. So here we have some equations. Remember that P1 is 3, P2 is 7, P3 is 11, P4 will be 13. So they are the prime numbers in ascending order. And we have this equation here where S is the number of cyclic prime terms or empty boxes, right, in a cycle. In this case, in the cycle from P1 to Pn, right? So the number of empty boxes in the cycle of P1 to Pn gonna be equal to the number of empty boxes in the prior cycle, cycle from P1 to Pn minus 1, multiplied by Pn minus 4. Why? Because that we studied already in this video that because of the combination process, all the empty boxes in one cycle, we're gonna combine with the empty boxes of the cycle of the prime number that is merging with the cycle. And any prime number Pn has a number of Pn minus 4 empty boxes, right? So the length, we have it here also. The length of any cycle is the length of the previous cycle times Pn. So the prime tens, or the per length of the cycle, this is cyclic prime terms of the length of the cycle, gonna be done by this equation. We're gonna obtain them by this equation. Or we can abbreviate it like here, like this. So now we're gonna pay attention to the formation of non-cyclic prime terms, okay? And that's done in the same combination process. So each of the 4 tens of any prime number cycle that has a number gonna combine with all the other ones of the cycle is merging with to form non-cyclic prime terms, not empty boxes. So we have always 4 not empty boxes. 4 boxes, 4 tens that they have a number. So when the cycle of 11, for example, combines with the cycle of 3 and 7, these 4 non-empty boxes gonna combine with the 21 boxes of the cycle of 3 and 7 to form 84 non-prime 10 combinations. Okay? But not only that, also the ones that are empty boxes in the cycle of 11, that they are 7, they're gonna combine with the 18 non-empty boxes to form more non-empty boxes. So we will have 4 times 21 plus 7 times 18, a total of 210 non-empty boxes in the cycle of 3, 7, and 11. The cycle of 3, 7, and 11 gonna go from 1 to 2310. And we're gonna have 231 boxes in that cycle, of which 210 gonna be non-empty boxes. I'm gonna have 21 that will be empty boxes. So you can see that the length of the cycles gets so big so quickly, but that doesn't matter because the questions we're gonna develop gonna be about the gaps, and really it doesn't matter how big they get so soon. The composition of prime numbers, the density doesn't change too much. When we do the combination process and when we combine cycles, we do it like this. The ones that has a non-empty boxes, like this one, the ones in gray, and the ones that they are empty boxes, that are the ones in white. And it's all about this combination. The beauty of this is that I don't care if in this empty box is a 1, a 3, a 7, or a 9 as the relevant multiple, right? Ended in those numbers, in those last digits. Doesn't matter. What it matters is the combinations, and when an empty box happen in the combinations of all the cycles that of prime numbers that gonna form a bigger cycle, right? So that's what it matters when we have empty boxes. Here it will be not necessary because we have to span this one here and this one 1, 2, 3, so probably will not be an empty box. But here we will have an empty box. And the beauty of this is that we don't have to care about if it is a last digit 1 or 9, and we don't have to care all about that. We care only about the empty boxes and nothing else. So to see what happens is what I call the main cycle. The main cycle starts with combining the cycle of 3 and 7, and we have a 210 cycle, right? with 3 empty boxes, 3 cyclic prime times, how I call it, and all the other boxes, all the other 10s are non-empty boxes. And when it combines with the cycle of the prime number 11, we're going to have 11 times this. You see here 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. And we're going to have the middle here, and there's going to be an empty box here in the middle. And we're going to have 11 of them. That will have all the empty boxes, the 3 empty boxes repeated 11 times, but minus the flips that the 11 gonna do to some of those empty boxes. Okay? And then we will have that cycle, the cycle of 3, 7, and 11. That will be look like here. This cycle now gonna have 21 empty boxes, and this cycle gonna be repeated 13 times to form this new cycle. With all the 21 empty boxes of this repeated 13 times, but with the flips that are going to be produced by the multiples, the relevant multiples of the prime number 13. And at the end, we're going to have the cycle of 3, 7, 11, and 13 from 3 through 13. That's going to go to 30,030. And so this is what I call the main cycle. It's a cycle that gets bigger and bigger because we keep adding by a merging process, like a fusion process. We keep adding to it another prime numbers, the cycles of another prime numbers. It gets getting bigger and bigger. Here we have something that is important also, that we have iterations of a cycle. Let's say this cycle, right? And from 0 to PM, right, gonna produce at the end, at beginning of each iteration, a section that we have no prime numbers. The prime numbers are here, but these prime numbers, for example, from 3, 7, 11, and 13, that will produce at the end here of this iteration a symmetric part to 3, 7, 11, and 13, a symmetric part that will have a place with no prime numbers. And at the beginning of the next iteration, this part here will have no prime numbers. So this one here, and this one here, and that's a repetition. So when we merge cycles and we get bigger cycles at the end and beginning of the new cycle, of the iterations of the new cycles, we're gonna be getting a bigger and bigger section without prime numbers. After the combination process, all the empty boxes or cyclic prime times, how I put here, there's going to be a cyclic prime time here, going to be from Pn to the symmetry of Pn here. So this Pn represents the distance from the end of the cycle to here will be Pn, right? So there won't be empty boxes in this area, and here there won't be in empty boxes. If you do an exercise and you do a triangle like, sorry, a rectangle like in the combination process, you will see why. So all of them will be from here to here, okay? And we will obtain all the empty boxes here. But remember that this part is getting so much bigger than Pn that is this we can disregard this aspect. So in the equations I'm gonna do it with the whole length of the cycle. So if I represent with a line empty boxes, It's funny because I always call it cyclic prime terms until the PhD that helped me start calling them empty boxes, and I think it's much easier uh, to call it empty boxes. I call it cyclic prime terms because for a cycle, it is like if they were primes, the four numbers that are in the term, right? So we will have a symmetry of prime terms, but we'll start from here on, from here on. We will never get a prime term here or here, okay? So let's continue. So how you can see the proposal of this study is that there is an infinite number of tens with four primes, what in mathematics is called prime quadruplets. So the study is based on this. So quickly, you can see here how evolves the number of cyclic prime terms per the length of the cycle in tens. So the length here is 210, but in tens is 21 tens, here 231 tens, right? And you can see if you continue this table and you do more numbers, you will see that the number of cyclic prime terms in this table gonna get more constant, like more constant proportion in relation to the length of the cycle. So we can see some convergences that we have to put in equations, right? Another observation is that you can see that the proportion of the gap per length of the cycle gets really, really small. But it doesn't matter because we can apply the symmetry equations to it, and we can disregard the rest of the cycle. And the proportion of prime tens to tens in the cycle, we can see it here, okay? Is the same. So here we have the equation of the gap length. Gap length will be the difference between the square of the next prime number Pn plus 1 that doesn't belong to the cycle minus the square of Pn. So if we have here the cycle of 3 through 19, that is the cycle of all the prime numbers 3, 7, 11, 13, 17, and 19 merged together in a single cycle. So Pn plus 1 will be 23, Pn will be 19, gap length, we do the difference of 525 minus 361 will be 164 as a gap length. And here we have the same thing with the cycle of 3 through 29. So subtraction of 841 and 961 will give 120. So because for every prime cycle of a single prime number, right, you're gonna have only 4 tens, 4 boxes that will contain a number. As we go up in the numbers, we are approaching a full of empty boxes cycle. So if we have a prime number in the trillions, you will have that trillion minus 4 will be the amount of empty boxes, right? So we are approaching the prime numbers that have a cycle full of empty boxes. That's our approach. So there is a tendency to convergence, some kind of convergence, right? Each empty box you will see it's gonna combine with each box of the main cycle, the cycle that has been already merged all the prior prime numbers, right? So for each empty box, it will combine with each box of uh, the the previous cycle of the merging previous cycle, the main cycle. And they will produce when the three, for example, here the three empty boxes will combine with all of these, and they will produce three identical repetitions of this cycle, of the main cycle. I call the main cycle the increased merging of cycles. So the first main cycle will be the merging of the cycle of 3 with the cycle of 7. And then the main cycle will be the merging of the cycle of 3, 7, and 11. And then 3, 7, 11, 13. But as we go up in numbers to the trillions, the coming next prime number will be approaching this as far as we go, right? So in this work, we focus on that, in that type of convergence, and the fact that we are approaching identical repetitions of the main cycle. That will never happen, but we're approaching that. So if the number 3 were full of empty boxes, that's not the case, but if it were, this will be the merging process. And you will see how you're going to produce 3 identical repetitions of the next cycle. This time will be the cycle of 7 that we showed in the last example. And so that identical repetition will come in this order, right? For the variable d, as a proportion of duplicate, how much we approach a full empty boxes cycle as we go up in numbers, you see how quickly approaches 1. So the merging cycle, the cycle that merges with the main cycle, is always will have 4 numbers in their boxes. All the rest will be empty boxes. You see how as we go up, we have more empty boxes in the cycle of the next prime number. So the cycle of P1 through Pn minus 1 gonna be repeated Pn times, right? So if we have the cycle of 3 and 7, when it joins the cycle of 11, is repeated 11 times. And the cycle of 11 gonna be repeated, gonna do 21 cycles, okay? And you see this is the length in tens, and we see how huge we gets the cycle so quickly. But that doesn't matter because the proportion of prime tens per length doesn't change it so much. It changes slightly. We know that already from number theory, right? For the length of the cycles, we have the following equation, this one here, that is the length of the previous cycle, cycle of P1 through Pm minus 1, times Pm. That will form the length of the cycle P1 through Pm, right? So we have this equation here. This is the length of the new cycle, and this is the length of the previous cycle times Pm. If we represent the number of empty boxes of cyclic prime tens, how I call it, we will have the variable s. So for the number of empty boxes of s from P1 through Pm for that cycle, right? This represents the cycle of P1 through Pm, the number of empty boxes. We will have that this will be the equation. So we will have the number of empty boxes in the new cycle form, P1 through Pm, will be equal to the number of empty boxes of the previous cycle, these empty boxes of the previous cycle, times Pm minus 4, that we already studied through the combination process, right? So as an example, for Pn equal 13, so we're going to find the number of empty boxes in the cycle of 3 through 13. 3 is P1 and 13 will be P4, right? So for the number of empty boxes in that cycle, we will have the number of empty boxes of the cycle from 3 to 11. So it's the cycle composed of the cycles of number 3, number 7, and number 11, times Pm minus 4. So we already studied that in the cycle of from 3 through 11, we have 21 empty boxes times Pm minus 4. That Pm will be 13 minus 4, and we'll have a total of 189 empty boxes. So we are dealing already with some equations, and the important about these equations is that they go up to infinity. We can analyze going to infinity for all cycles, right? Here I have an equation that really is an approximation. So as prime number gets bigger and bigger, we are approaching, as we said, a full of empty boxes cycle, and I can get rid of this 4 here, so we will have this as an equation for the number of empty boxes in every new cycle, right? So also we have this as the equation of length for every cycle, that is the length of the previous cycle times Pn will be the length of the new cycle, right? If I make a proportion here of empty boxes divided by the length, we see that both are multiplied by the same number, by Pm. So the number of empty boxes per length of the cycle is approaching a constant. And really, as we said, the empty boxes goes from 2Pn to the length minus Pm, right? As we study in other slides of this. But this is a very fair approximation, taking the whole length as the length where the empty box is gonna fall, right? So this approximation tells us that there is kind of a convergence, but this is not enough, obviously. So we're gonna keep going. Here we have the cycle of 3 and 7 in this sketch. The vertical lines, they mean the empty boxes on the cycle of 3 and 7. You can check the cycle in the previous slides. And if you remember, it had 2 empty boxes at the beginning in the second box, and in the before last one, right, box, and then one in the center. All cycles have an empty box in the center. So this is the cycle of 3 and 7. So when the 11 comes and make a merge with the cycle of 3 and 7, there are going to be 11 repetitions of the cycle of 3 and 7, but we have to take in account the flips of the cycle of 11. So there are going to be some empty boxes that they're going to stop being empty boxes because they're going to have a multiple of 11 ended in 1, 3, 7, or 9 in that box, right? So we'll stop being an empty box. So if we don't take in account the multiples of the cycle of 11, these are the 11 repetitions of the cycle of 3 and 7. The vertical lines are empty boxes. And these ones, the ones that are bigger, are the middle empty boxes of each iteration of the cycle of 3 and 7. So we have 11 iterations. So here we have again the 11 iterations of the cycle of 3 and 7, but the cycles are the flips of the cycle of number 11. So these empty boxes, these cyclic prime times, we have a multiple of 11 ended in the relevant multiples. So ended in 1, 3, 7, or 9 in that box. So it will stop being an empty box. There is an exception in the first empty box, this one here, because we're gonna have 11 there. So in that empty box, we will have an 11 as one of the multiples of 11. But 11 is already the prime number, so doesn't get flipped. It's gonna get flipped. This box gonna get flipped in each of the next iterations, in the second iteration, third, and so on. So if we take out the empty boxes that contains multiples of 11, because they don't wanna be empty box anymore, this is what we get. And this is the cycle of 3, 7, and 11. Cycle of 3, 7, and 11. And that's the empty boxes of that cycle. And they will repeat in each iteration forever, except this one. This one won't be an empty box in the next iterations, because because it's a multiple of 11. Here is the 11 per se, as I explained already. But we can see here also that the separation between empty boxes, or eventually between prime terms, because the empty boxes is what are gonna make the prime terms, is due to the flips of the coming prime numbers. And all of them are repetitions of the cycle of 3, all of them are repetitions of the cycle of 3 and 7, but with added spaces by the flips of the coming prime numbers. This is the combination of the cycle of 3 and 7 with the cycle of 11. They are merging and they will form the cycle of 3 through 11 that goes from 0 to 2310. And we have to be careful in this combination flow process. We're gonna check when the empty box is gonna appear. For example, the combination process goes like this, always in diagonals, right? When there is an intersection of two empty boxes, they will form an empty box. So here, this one here meets in the diagonal with this one here. So this will be one of the empty boxes. So there is something that we gotta notice, is that in the second one, this one here, in the second one, we know this will be always a prime term. But this doesn't count as the amount of empty boxes in the cycle, because this won't be an empty box in that cycle because it's a multiple of 11. Even 11 is a prime number. It's gonna continue to be a prime term, a prime quadruplet, but it's an exception because this gonna get with this one, and how you can see this is where the 11 is contained. So this doesn't gonna be one of the empty boxes that in our equation is gonna be reflected. That's why we already explained that from PM to the length of the cycle minus PM, right? All the empty boxes in the equation is gonna be contained. But we're gonna be accumulating prime quadruplets that they will won't show in the equations. They're not gonna be reflected in the equations. Okay, but this is the way we're gonna keep doing after we do the combination of this. So when this finish here, for example, then it's gonna continue here. And then from here we're gonna continue until all the diagonals are filled and we have the next cycle. And then that cycle from 3 to 11 gonna be put together in this axis, and we're gonna combine with the cycle of number 13 in this axis, and we do the same process. Okay, so every new cycle is several repetitions of the previous one, repeating its composition as many times as units of the new prime number. There is no extra space generated at all because all are repetitions of previous cycles. All of them are multiple repetitions of the cycle of 3, and the cycle of 3 is always the same size. The increase of distance of prime tens and prime numbers is due to the flips generated by the continuous coming prime numbers that form the new main cycles. It's very important to remember that the flips are always multiples of the coming new coming prime number multiplied by itself or by other prime numbers bigger than itself. Because, for example, if you have the cycle of 3 and 7 and comes number 11, the flip's gonna be from 121 and up, because under 121 the multiples of 11 gonna be already multiples of 3 or 7, so they are already included in the cycle. So the flips gonna be always multiples of the new prime number that gonna be merged with the main cycle and itself or other bigger prime numbers. So when we are in the hundreds, look, this is gonna be the distance between flips. So this will be a one flip and this will be another flip, and we're gonna have a distance of minimum of 200. We can have bigger distances because they can be separated by more than 2, but that's gonna be the minimum distances. But already in the tens of thousands, look, the distances 20,000 already between flips. So remember, the empty boxes are converging per unit length in the cycles. Doesn't mean in the real number line, but they are converging in the cycles per length. But the flips are getting bigger and bigger in the distance between them, right? And that's something that tells us that we are reaching convergence in different aspects. In this graphic, we are seeing the formation of the gaps. These are all the individual cycles that will merge with the main cycle to form the next main cycle, right? So PM minus 4, PM minus 3, and these are the gaps that they form. Here there is the gap of the fusion of the PM minus 4 with the main cycle, and this one will be of the PM minus 3. And here we have the PM with PM plus 1. So this is the distance that the gap is forming, right? In this gap is the what we add in the main cycle, the piece that we add, that we will know that the compositions of the prime numbers in the real number line will be the same as in the gap and in all previous gaps, right? So in the main cycle until here, will be the composition. And then when comes the next PM, right, will be until here. And it continues so on. So as this study, we are proving that there will be cyclic prime times or empty boxes in the gaps. If we prove that there will not be empty boxes in the gaps, we are proving not only the twin prime theorem, we are proving that there is an infinite number of prime quadruplets, and I will say that we will prove even more than that. These are the equations for the proportion of empty boxes in the gaps. This equation here, for example, these two here, these are the numbers of empty boxes in the previous cycle, and this is the length of the previous cycle. When we're gonna multiply with PM minus 4 as the combination theory that we study in this work, we will get the number of empty boxes with this multiplication, PM minus 4 times the number of prior empty boxes, and Pn times the length of the previous cycle will be the length of the new cycle. So this whole term here gonna tell us the number of empty boxes per length of the new cycle. This is a proportion. When we multiply by the length of the gap, we will have the proportion of empty boxes in the gap. We know that not necessarily that the gap gonna have that amount of empty boxes, but we are making just a proportion, and we will see why later. This is a universal equation for the number of empty boxes per gap, and I is the increment, I mean the separation between the prime numbers that forms the gap. So if the separation is, let's say, like 6 from 23 to 29, I is 6. Okay? Let's continue. So we are studying the gaps by their classes, so by the separation of the prime numbers. So for gaps that the separation of the prime numbers that forms the gap are of 2, like 11, 13, 29, 31, 101, 103. This will be the equation. And we're going to do it like if they were consecutive gaps of plus 2. That's not real, but because we don't want to have two consecutive gaps of plus 2, but we are doing this just to see how the equations behave. And we will see the importance of that later. Here, you see the equation of the empty boxes per length, and because we are dealing with gaps of plus 2, so that the separation of the primes is only 2, we have Pn and Pn plus 1. So Pn plus 1 gonna be equal to Pn plus 2 because it's minimum separation. So we have here Pn plus 1, we have here Pn, and when we make the simplification, we get this with the 4 here, very important, and Pn plus 1 here. And now we continue with the next consecutive gap of plus 2, so we can make a proportion. That's not real, as I said, because we can take like 11 and 13, and then the next will be 13 and 15. 15 is not a prime number, but we are doing this to see how the equations behave. We don't gonna be able to get any 3 consecutive primes just separated by 2, right? But this is the equation. So Pn plus 1 was already, is here now, that is Pn plus 2, and Pn plus 2 will be Pn plus 4, so it's there. And we get again this factor, but we gotta add one more factor of this, so we get this, okay? If you substitute there Pn plus 1, you're gonna get this. And if we simplify, we get this. And we make the proportion of the higher gap, proportion of empty boxes with gap with the lower. So this is the proportion. This equation here is on top, and this equation here is on the bottom here. We make the proportion, and we can see that this is gonna be less than 1. So if we will have consecutive prime numbers separated by 2 up to infinity, the proportion of empty boxes per gap gonna get smaller and smaller, gonna get lower and lower. So gaps of +2 don't gonna help in making more the proportion of empty boxes increase, right, per gap, proportion of empty boxes per gap. Let's continue. We do the same process for the gaps of +4, +6, and +10. We can do it +8, I didn't do it, but if we do the same process, you can see that there is an inflection point here between the +4 to +6. Gaps of +4 always decrease the proportion of empty boxes per gap length. If we have consecutive gaps of +4 all the time. And in gaps of +6, we get an increase, so there is an inflection point here. You can see it in the universal equations that I did 2 or 3 slides ago, that will happen always. So as we get more gaps of +6 or bigger, we're gonna get an increase in the proportion of empty boxes. And that's because the increase in gap size as Pn goes bigger gonna become more important than the decrease of empty boxes per length in the cycles, because the empty boxes per length will always decrease because there are gonna be always flips, and you're gonna have always of empty boxes that will stop being empty boxes. So there is an increase always, but gonna be less significant than the increase in the gap length, because Pn is getting bigger and bigger. This is a very important observation. This equation really converges very quickly, but what we are interested is this one. This is the one that really affects everything, because it's the multiplication of all the factors of empty boxes per length of cycles, making this proportion more important. As we get more factors, the factors of +2 and +4 are gonna make this decrease, but the factors of +6, +8, +10 and up are gonna make this increase. And how you can see, this converges much more slowly. You see, the convergence is slower when this one converges much more quickly. So there is a delay because you are adding a lot of factors in the convergence. So for gaps of +2, we have here that if all the numbers were separated, all prime numbers, by 2, you can see that how this is going smaller and smaller. The gaps are getting bigger, but the proportion will always get smaller. So as I said, gaps of +2 doesn't gonna improve, doesn't gonna raise the empty boxes per length in the gaps. Here, in gap of +10, you can see that this decreases also, but the gap increases largely, and this is increasing. The number of empty boxes per gap are increasing, or prime terms, because if an empty box is in the gap, it's gonna be a prime term, a prime quadruplet, right? And this is the table of the real number line table. You can see how this gets smaller, like always, gaps increases, but this column fluctuates because you have gaps of +6, you have gaps of +2, +4, and this start fluctuating, +8. And that's what we are focusing, because this is gonna be converged. And doesn't matter the order of the factors, it comes a +2, +8. The order of the factors don't gonna alter the result, and we're gonna be getting more gaps of +6 and over, +8, +10, +30, because for every new prime number there are gonna be flips, and they're gonna be increasing distance in the prime number, so they're gonna be increasing the of distance in the gaps formed by those prime numbers. So here we have the vertical lines are empty boxes. This is the main cycle, main cycle 1, main cycle 2, 3, 4, 5, until 8. You can see that the gaps will be, these will be the gaps, right? This is to explain the logic of everything. As the longer is the gap, the flips of the next cycle will not affect anything of the gap, right? So you will, as longer the gap, more proportion of prime tens, of cyclic prime tens or empty boxes per gap. So you're gonna have more empty boxes as longer is the gap. That's why bigger gaps with more separation of between the primes that form the gap will have an increase in the proportion of empty boxes in their gap. And smaller ones, they will not catch as many empty boxes. Quickly comes the flips of the next, you see? You have here, but here comes the flips, so you will have a decrease in the empty boxes per length of the gap. Here we have a fictitious prime number, hypothetic prime numbers. Especially from 55 on, they are not prime numbers, but I chose number 55 like if it were a prime number. I should have shown another number, but I chose another number, but I chose 55. The thing is that it's not important because we are just wanting to see how the equations behave. And we have two gaps of +2 because 55 to 57 is a separation of 2, 109 to 111 is a separation of 2. So from, if you see, in the middle they have another gaps that they are bigger. From 57 to 67 is +10, then +20, then +6, and then from 93 to 109 is +16. So the proportion of empty boxes of cyclic prime terms per gap in gaps of +2, it increases, of course, due to the other gaps that are in between. And this is important to know that when we go to billions, trillions of numbers, there are going to be a lot of gaps of +10, +20, +30, and more. And we see that even the gaps of +2, they're going to be increased from one to another one, right? Because they are affected by this factor here, all these factors, right? They're gonna affected by the different factors of the other gaps. So this is we are pointing to a convergence and to a moment that practically all gaps, from gap to gap, the proportion of empty boxes per gap gonna be increasing from gap to gap, even in the gaps of +2. So we are looking for that type of convergence. To better understand it, let's take a distance of 100 and compare the evolution of the factor Pm minus 4 over Pm versus the evolution of the length of the gaps through different compositions of primes within these 100 units. Let's say one composition consists of primes separated by short distances and another by large distances. We will designate them based on their prime separations, such as +2, +4, +6, +10, +26. And these separations will add up to 100. First composition is this one. You see there is small separations, +2, +4, +2, +10, for a total of 100. And the second composition are gaps formed by separations of the primes of +14, +10, +26, +22, +28. Again, for a total of 100. So these will be the separations of the prime number. This +2, +4 here, +2, +10. And we can see that this is gonna add 100. And so you're gonna have a lot of factors of this. You're gonna have for each separation, you're gonna have one factor of this. So you're gonna have multiple factors. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. You're gonna have 18 factors of this. Every time you have one factor of this, the separation of prime tens increases, right? Because more prime tens are flipped. And here, because the bigger separations, you have only 4 factors. 1, 2, 3, 4, 5. 5 factors. So here you're gonna have less separation of prime tens, because for the same distance, for 100, you have less factors, so you're gonna have much less prime tens flip than in this one up here. Okay. Looking to the data, we have here prime numbers at the billions. We can see big separations here. For example, there is a separation of 18 here. At the beginning, there is a separation of 16. The important thing is that it's a process that doesn't go backwards, always goes forwards, and separations between prime numbers will continue to increase. This is the second and third iteration of the cycle of 3 and 7. And we have here the empty boxes per gap in this column and in this column. This is the second iteration, this is the third iteration. Here are the potential prime numbers. If we pick the corresponding gap from one iteration to the other one, so this is the first gap, the one 221 to 223, and this is the first gap of the third iteration, 431 to 433. So I say that they are corresponding gaps, and we see that, as expected, from one gap of +2, because this is a gap of +2, to the second gap of +2 in the third iteration, there is an increase, 0.38 to 0.41. And that happened with all gaps of all sizes, even gaps of +2. That's the important thing. So, and we know that these are potential prime numbers, but in the real number line, spaces between primes are gonna be bigger. Uh, so we're gonna have more of an increase. If we look from the same iteration, one gap of plus 2 to the next gap of plus 2 here, there is a decrease. In gap of plus 2 and plus 4, there is a decrease in some of them. In gap of plus 6, we see an increase. Remember that the important thing is this factor, so that is included in all the calculations of empty boxes per gap, right? This is the factor that is important. So from here to the next gap of plus 2, there is a decrease. But in the next slide, I have the complete iterations. So these two slides are the whole two iterations, second and third iteration. And we're gonna see that from here, 0.3842, for example, to here to 269 is 0.3830. So the decrease is smaller. And if we go here, is still smaller. So let's check in the next slide so we see the rest of the iterations. Remember the first gap of the second iteration in the previous slide was 0.384. But if we go here to the end, we have in 401 a gap of plus 2, and we have 0.4. There is an increase already. So this means that in the real number line from a gap of plus 2 to another gap of plus 2, gonna be an increase already as we go further. And this is just two iterations. These are not the real number line. In the real number line, spaces between primes gonna be bigger than in these two iterations. So there definitively gonna be an increase from a gap of plus 2 to another gap of plus 2. If, this is very reasonable and this is very logical that there's gonna be a point that there's gonna be an increase in the proportion of empty boxes per gap for all gaps as we go further. Remember, this is only the iterations of cycle of 3 and 7. Imagine when we have cycles of 1,000,000,000 numbers, that they will be iterations of the cycle of 3 and 7, but with a lot of flips, with bigger distances between prime numbers. So if you think about this and you analyze well, you will realize that there is an increase in the proportion of empty box per gap. And with the rest of the analysis, we know that that's gonna be happening, that those empty boxes gonna be there in the gaps, so they will be prime quadruplets. So let's continue. When I was analyzing this work with the PhD of mathematics, he told me about my previous slides, right, that there was not a demonstration, that I had separate equations for gap of plus 2, plus 4, plus 10, plus 8, but he didn't see a demonstration. I don't know if he understood me completely what I was saying, but to me it is a logical process. He told me that logic is valid to make a proof of something in mathematics. So if that's the case, to me, it's very logical what I said. And if you study two iterations and you find an increase in two consecutive iterations of a cycle, from the second to the third, you know that there's going to be an increase in the next coming main cycles and iterations, because it's a process that goes forward and you're going to have always more flips, so you're going to have an increasing space between the prime numbers. So to me, it is a proof that, or it is something logical, I don't know, because I'm not a mathematician, I cannot say if it is a proof really, but It's a very logical process that all the gaps, there are going to be a moment uh, when I analyze the gaps of the cycle of 3 and 7 from the two iterations, it makes very clearly that there's going to be a moment that from gap to gap, even gaps of plus 2, there's going to be an increase of proportion of empty boxes per gap. And in the next slides, we analyze why those empty boxes gonna appear in the gaps. Because of course, when we say empty boxes per gap is a proportion, taking in account the whole length of the cycle and the number of empty boxes in the cycle. But there is some facts that tells you that necessarily they're gonna appear in the gaps, the empty boxes. So we will explain that next. As we see in this graph, this is the part that we know the composition of prime numbers in a cycle, and this is the whole cycle, and the rest we don't know the real composition of prime numbers because we don't have a lot of potential prime numbers. But this is going to be very tiny compared to the cycle. But what we know is this gonna have a lot of potential prime numbers, and when we go to the next main cycles, a lot of them, we're gonna have more spaces between prime numbers in the rest of this, right? So when we compare gap to gap in a cycle, we know that in the real number line, there are gonna be more spaces, so the gaps will have more empty boxes. The proportion of empty boxes per gap will be bigger. So the next slide, like I said, we're gonna explain why those empty boxes gonna be appearing here in the part that we have the non-composition of prime numbers. In this graph, we show the progression of the main cycle. So we have cycle 1, cycle 2, cycle 3, up and up. Each cycle has a fusion of another of the next coming prime number cycle, right? So and each vertical line, it represents an empty box, a cyclic prime time. So we have the gaps here for each new cycle, each new merging of the main cycle. And let's suppose that in the first gap there is no empty boxes. There is one here, but let's suppose there is no one. So then it comes to the next prime number and the fusion of the next prime number, and this will be the next main cycle that starts here, but here starts the flips of the next prime number and goes all the way up to infinity, right? In iterations, right? So let's say here in this gap there is neither another empty box, so there is no empty box either, because if we remember, the empty boxes in the gaps is a proportion. The empty boxes has a proportion of the length of the cycle, right? A number of empty boxes per length. So it corresponds a proportion to the gap, but prime numbers not necessarily behave constantly. So it can happen that there is no empty box in the first gap, and it could happen there is no empty box in the second gap, also, and so on. But if you see, the second gap is formed by the next segment of the first gap, of the cycle, of the main cycle of the first gap. with the extra flips of empty boxes of the next prime numbers that merges in the second main cycle that represents the cycle that forms the gap 2. And then it comes the next main cycle, that is the fusion of the previous cycle with the next prime number and its flips. So in the gap 3, we have the extension of the gap 1 and gap 2 of those cycles with the extra flips of the prime number that forms the main cycle corresponding to the gap 3. So because it's an extension of the previous main cycles, there gotta be a moment that the parts of the main cycle of gap 1, gap 2 gotta be a moment that they will reflect the parts that have more empty boxes. Because if in the gap 1 doesn't reflect the proportion of empty boxes, neither gap 2, eventually this is a continuous process up to infinity, adding gaps. Eventually will come those parts, right? That will reflect more empty boxes. You can say, of course, that, well, maybe each new main cycle, the prime numbers that form it and makes the flips, will be flipping exactly the, the empty boxes for each gap. Yeah, that's possible, but we know that cannot happen. I mean, uh, in the process of forming main cycles, we know that all the flips are gonna be first extended all over the length of the cycle, because there are multiples of the coming prime numbers, so they're gonna hit. If you have in the trillions, they're gonna hit flips every trillion, and not necessarily those flips gonna be empty boxes, could be other ones. So that's really unreal, because if we have studied already the process of how the cycles form, and really from the start of the flips of the prime number that forms the cycle to the end of it, there is not any preference for the gap that will be always hitting the empty boxes in the gap. We know that's a chain, and that they cannot be hitting all the time um, in one place of the, or at the beginning always of the cycles. They're gonna be hitting every multiples of the prime number that is merging with the main cycle. So as they behave, as the prime number behave, it do it erratically, like the Gauss prime function, right? Uh, but at um, at a whole view, we know that it behaves like a function. We see it in big spaces, right? So we know that flip is gonna be symmetrical distributed along the cycle, along the cycles. We have to remember that the number of prime times, or cyclic prime time, or empty boxes, is equal to the previous number of cyclic prime times of empty boxes times the new prime number minus 4. But we also know something, and it's this 4 here. It's very important. The flips of empty boxes. So we're gonna put here flips of S of empty boxes gonna be equal to the empty boxes of the previous cycle times 4. This 4 here is this 4 here. What that tells you? That every length is multiplied by Pn, while this tells you that it's gonna be a much less proportion of empty boxes per length of the cycle, because this is the length is multiplied by Pn, while this is only multiplied by 4. So the flips are gonna be less and less per unit length, while the empty boxes in the gaps, as we study in this video and in my paperwork, is increasing and converging to 1. If you see the data in the prime numbers, the data we have primes until billions, and you calculate the number of empty boxes of prime tens in the gaps, you're gonna see that all of them have 1 already. Already in the billions, you calculate that, and all of them gonna have at least 1 and maybe 2. So my prediction, really, I haven't demonstrated that, right? But my prediction is that the average number of empty boxes per gap gonna converge to a number, I believe, gonna be over 1, probably over 2. And that will be an interesting calculation, maybe with computers, can be done. Remember that all the cycles are repetitions of the previous cycle. So once you have an average of 1 for an entire cycle, in the coming cycles that's gonna happen always, because for every merge you're gonna be increasing the distance between prime numbers. They will never decrease, and that will make that the next repetitions or the next portions of the real number line gonna have also prime terms, prime quadruplets, and they will be constant. I think there is a constant. We will approach a constant of empty boxes per gap. So this tells you that there is a lot of potential for research here. I think this is a breakthrough. I think it's a breakthrough in the sense that there is a lot to research here. I'm making it available. My first priority, of course, is finding a mathematician that can help me to write this so it can be accepted in a journal. Already mathematicians that have seen this, they told me they can help me to write the first part, the arithmetic part, modular arithmetic, but they are not experts in number theory, so the rest gotta be, I gotta find somebody. So probably if I find somebody, I will take him to make the whole paperwork, right? So if you find somebody interested, just contact me. So let's continue. So I have been playing with another concept. In these graphs, we can see here that the bigger lines are already prime quadruplets or prime tens, how I said, And the smaller ones are empty boxes that we don't know if they're gonna be prime quadruplets at the end or no. And when we have several gaps, let's say, we know that maybe there is gaps here. These are gaps. So when it came here, it catch this and there was no flip, so sorry, just a moment. It catches this, there was no flip, so this became a prime quadruplet. And let's say we can see here that they have several uh, gaps until the next empty box. So there is a limited number of flips that can flip this empty box because you have a limited number of prime numbers here that can flip the empty box. But it can happen that also if you have only like it is shown the real data of the prime quadruplets, you have only one gap until the next empty box. So imagine we have only one gap and there is some that you can have more than one empty box. We don't know if they're gonna flip these empty boxes, but we know that even if they flip one of the empty boxes and there is only one gap, it cannot flip both twin primes in the same empty box because there is only one prime number, and if the prime number is into the billions, the flip's gonna be separated by billions, so it cannot flip two twin primes in the same 10 because the flip's gonna be separated by billions. Uh, and if there is several, 5, 6 gaps before the next empty box, there is also a big separation um, between the flips of the prime numbers. Imagine you have like here um, 5 empty boxes until it catches the next. Sorry, imagine you have 5 gaps until it catches the next empty box. Okay, let's imagine that. And we are in the billions. Yeah, it could happen that two flips fall in the same 10 and flips two twin primes, but that's we know that that doesn't gonna happen in our way to infinity for every gap. And really, if you check the data, like I said before, you're gonna find always in each gap a prime quadruplet. Once you calculate, oh, there is another prime quadruplet and it's only one gap, and there is some of the gaps that they take two prime quadruplets, and we know that that's gonna keep happening because what I already explained in the previous slides. So in conclusion, we know that there is an inflection point in +4 to +6. We know that this is a process that we're gonna have more and more um, gaps of +6, +8, +10, and over, because for any new prime number, we're gonna make separation of prime numbers. The separation of prime numbers is gonna be bigger, and this tells a lot. This equation, um, the order of factors here doesn't gonna alter the result. So it doesn't matter in which order comes the gaps of +2 or +8 or +20. We know we're gonna have more abundance of those, and this gonna be converging uh, to an increased number of empty boxes per length in the gaps. So we're gonna have more empty boxes per gap, limited. Remember, not per length of gap. Per gap, we're gonna have more empty boxes as we go up. That's gonna converge. I think there is a number that we can look for it. Mathematicians can look for it. And the length of the gap always gets bigger. And this is gonna be more important than the flips of empty boxes. And this is gonna be dominant. So this is what gonna make that we're gonna have an infinite number of empty boxes, because they will always appear in the gaps. Also very important that the equation I said before, that the number of flips of empty boxes is the previous empty boxes times 4 only, while the length of the gap of the cycles gonna get bigger and bigger. I say we're gonna have empty boxes in the gaps, and the opposite cannot be true. So we can work with that mathematic approach, that if we look at the opposite and it's not real, it's not probable, the probable thing is what I'm saying, that the empty box is going to appear in the gap. Because the opposite thing is that for every new gap that's going to contain empty boxes, always the multiples of the new prime number are going to hit the empty box. And that's not probable. Gaps gets bigger and bigger until trillions, and gonna hit the empty boxes. You're gonna get more empty boxes per gap until probably, I cannot be sure, probably a convergence to a number. But I think it will be a convergence to a number. Expert mathematicians can work in this if my analysis is correct and if it's worth for you, if you think it's valuable. So thank you for watching. I hope experts in number theory, I really need help if you think it's worth it. See you soon. Thank you. So an interesting analysis to me, I don't know if mathematicians will agree with anything that I'm gonna say about this, but if we look, the cycles are symmetric. They have a empty box in the middle, and they have empty boxes both sides of the middle that are symmetrical, that they are separated, and in the real number line we have the prime quadruplets, or prime tens, how I say. So I think that the real number line, in a philosophical way, we can say that it is approaching an infinite cycle, where at infinity we have an empty box in the middle, and the point is that the prime quadruplets, or empty boxes of the real number line, they gonna be getting apart more and more, and always like imitating a cycle. It's like a big cycle, because remember that all the prime terms, I mean prime quadruplets in the real number line, they gonna be always increasing the distance between them. Doesn't matter that the number of empty boxes per gap, or the prime times per gap, will converge, because even if it converges, and if the mathematicians agree that they converge, they're gonna still
uh, increase the distance between prime quadruplets, because the convergence is per gap, not per distance, because the gaps are getting always bigger and bigger, I mean longer and longer, because the difference of squares of the primes, of consecutive primes, is getting always longer. So that will make that there gonna be an increase in distance between empty boxes in the real number line. So we're gonna have at the beginning closer empty boxes, and as we go to infinity, the empty boxes per gap converges, but it will always gonna be increasing. Doesn't matter that the empty boxes um, converges per gap, because gaps are getting bigger. So this will happen the same in both sides, right? Uh, so it's really interesting that. And another interesting thing is that if you see, there is at the beginning a 1 here, and there is a 9 here. And for every cycle, if we have a second iteration, the 1 here, the last 9 here at the end of any cycle, and the first 1 here at the beginning of the second iteration of any cycle, they're gonna be potential primes, always gonna be potential primes. And if you see, this is completely symmetrical to this. So really, if I put myself here and I look this to a perspective to this side, this can be a 1, a number ended in 1. And I can change the 3's for the 7's and the 9 for the 1's, and we will have this identical as the same thing. We can imitate this. So what is this? This, we can say that at the middle is a infinity is an empty box at the middle, because the numbers behave like that. And we can say that this could be the negative numbers. The negative numbers. So when it starts another iteration here, right? We can say there is an endless um, number of iterations that could be another system of numbers. To me, as a philosophical way, it fits with multi-universes, right? Or we can have just a loop or only one. That's just playing with ideas, right? So I don't know if it has something of value, but to me it's interesting. So thank you for watching. I hope somebody contact me, somebody tell me things about this, what they believe, any mathematician, and I open to any opinion. And thank you. Take care.